तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Today's discussion on numerical methods in programming, we will focus on the modeling data in using a fit. Okay. So, last time we discussed modeling data using interpolation. So, that is we do. So, if you have a set of points, this is what we did last time. So, if you have a set of points, let us say a function of x as a variable x, and then if you have a set of points, and then we would say that if the so we got some set of points like this in some from some measurement, and if you have full confidence on the on this data, that is if you know for sure that these data points are reliable, all these variations in the data points are actually reliable, are actual variations, and then we would have what is called an interpolation, right. So, then we would have an interpolating data which would just go over all these data points. So, that is what we saw in the last few classes, that how to construct a line which goes through all these data points. But let us say in many cases we do not have we do not believe that this fluctuation in the data is actually real, okay. And all we want is an average line which goes through all this point. So, in that case we use what is called data fitting. So, we have a functional form which we believe represents the correct data, and we want to just fit that function form into this set of points. So, that is what we would be using, we will be discussing in today's lecture. How do one do that? Okay, there are two occasions. One is this data is not very reliable, and so all these fluctuations may not be a real fluctuation, it may be some measurement error. So, the reliability of each of these points has some finiteness. And on another case is that we know the functional form. Okay, many cases that happens, we know the functional form, and then we want to know how that data would fit in. Okay, so, as we saw in the case that we could have for example, if you have some curve like this, we could have, if you have a polynomial interpolation, we would have some curve which goes like that. Okay, so, that would be a polynomial kind of interpolation, if we believe that our function should go through all these points. So, that is what we use if you actually believe that these fluctuations are real, and if you want to evaluate, or if you want to know what is the function value at any point in between here, okay, or here for example, what is the function value, and then we would use what is called the interpolation. But as I said, so some cases we know that this is not supposed to be fluctuating, and we know and this is due to some measurement error or some numerical error, if the case data comes from a simulation or a numerical calculation, or it is because of some measurement error if it comes from some experiments. So, and we believe, and all we want is just to get a smooth curve which goes through all these points. Okay. So, here is a smooth curve which goes through all these points, and that is all we are interested in. We are not actually interested in the actual fluctuations of the data. So, how do we do that? Okay. So that is what we would do with the fit. Okay. So, to summarize, so So if you have a given set of discrete, if a given set of discrete points, okay, so we can either interpolate or we could fit. Okay, so that's what the two methods are. Okay, and now we are looking at is the fit. Okay, we looked at the interpolation, and now we look at the fit. Okay, and used mainly when the two cases mainly when we don't have full confidence in the accuracy of the data given, and another case that we know that it should look like a certain function with adjustable parameters. So if you know that the data should actually look like a certain function with adjustable parameters, okay, then this f of x, let's say this f of x actually has some adjustable parameters a1, a2, a3, etc. These are adjustable parameters of this, and then we could actually try to get this curve by adjusting these parameters and try to get the best curve which goes through all these points, or a function which best represents this set of data points. So that's the idea of doing a fit, okay, to get this function which get a function with adjustable parameters, okay, and by adjusting those parameters we want to get the function which fits best to this data, okay, which is the best fit to this data. Okay, that's what we want to look at, and the question is how do we get that, and what is the quantity which tells us that something, this is the best fit. Right? So that's what we would be looking at in today's lecture. Okay, so here is an example. Let's say that there is a quantity eta, okay, which we know as eta, we know behaves like, you know, some constant times, or eta is proportional to t to the power of alpha. Okay, and we are only interested in basically what this alpha is. This is a very common occurrence in science. Okay, so that we have some measurement eta, some quantity, okay, which varies with time or temperature or whatever, some variable as eta to the power of t, eta goes as t to the power of alpha. So now if you do a typical measurement for this eta, or a typical simulation calculation for eta, we would get a very fluctuating curve. Okay. So then from that, now if you could plot, so now from that we need, all we need to do, or all we are interested in the experiment, is to actually extract this alpha. Okay. So that's what I said. So you could have, as I said, this function could be some, you know, a1 x squared plus b2 a2 x cubed plus a3 x to the power of 4, or something like this, some function like this, some polynomial function like this. Okay. And we are interested only in a1, a2 and a3 values. We know it is a polynomial. Let's say we know it's a polynomial, and all we are interested in is a1, a2, a3 values. We are not actually interested in getting the full functional form, otherwise we are not interested in getting the whole representing these fluctuations. Okay. Another case which I said here is that we say f of t is equal to, well, let's say we are interested in some a t to the power of alpha. Okay, we are interested in that, and we are only interested in this exponent, okay, alpha. We are not interested in this whole variation of this quantity. Okay. So in that case, how do we do this? Okay, so that's the case which we look at it. So now if you actually do a measurement, and what we find is that if you in an actual measurement, this function might look like, you know, a set of scattered data points. Okay. So I have taken f of t as, or the function which I call eta in that particular case. So I am taking this function eta as a t to the power of alpha. Then I am taking the log of that on either side. Okay, so that would be equal to some, right, log of a plus alpha log of t, right. So, and I am only interested, so I know that this goes like a, so as if I plot log eta versus log t, right. So I take log eta versus log t, then that's a straight line. This is a constant. So if I take log eta and plot, if I take log eta on the y axis and log t on the x axis, I would get it as a straight line. That's what I would expect. But in a typical experiment, what I would get is a set of scattered data points. Right. So I'll get a lot of scattered data points, and I know that it should behave as a straight line. So I try to fit a straight line through this. I guess I try to draw a straight line, And then what you see is that if I by visual inspection I can't do this, because I have drawn 3 different straight lines which all looks more or less going through these points. Okay, so that's not a good way to do it. So we should have a correct some quantitative way of measuring this, that which is the correct line which goes through this set of points. Okay, so that's what we should be trying to estimate. So we should try to estimate an error, and then we should try to minimize the error. Okay, so some with a quantity called a fitting parameter, a fitting error. Okay. So that's what we would be looking at. So we will try to now quantify this a bit and then do this. So let's move. Let's say that we have a set of data points xi and yi. Okay, so yi is so xi is the independent parameter and independent variable, and yi is a measurement. Okay, so it's a function of time. Some as a function. This could be time, temperature, or something, and this is some quantity which we measure. Okay. So then we need to fit some, let's say some curve f of x through this. Okay, so the curve which we want to fit is f of x. Okay. So if everything is true, and if what the fit is there is no fluctuation and everything is correct, then what you would get is that y is equal to f of x. Right. But y is equal to f of x is the real curve which we expect to get. Right. So, but the measurement or the simulation data gave us xi and yi. Okay, so for each, so what we got y of xi, so this yi is the measurement and xi is the variable which we changed. Okay, and now we want to fit in a curve through this, and let's say we have adjustable parameters ai's. Okay, so our adjustable parameters are ai's. Okay, so that's so this is the real function. Let's say that's a real function, and that is the measured value. Okay, and we have ai's are the fitting parameters. Okay. Okay, so ai is the fitting parameter. So that's what we have. Okay, so we have some function, some set of data points, and we want to fit in a function y equal to f of x type, okay, through this data points, and ai is our fitting parameters. So the question again to formulate is that what is the values of ai, right, which best represents this data. Okay. The function is given to you. Okay, the function is already given to you. Okay, so there is nothing to determine there except this parameters ai. So what are the values of ai which best represents this data? Or another way the question would be is that if I write this function with a set of ai's, what is the probability that the measured values will be close to that function, okay, that calculated value of plus minus delta y. Okay. So these are two questions we can ask. One is, given these data points, what are the values of ai which best represents this function? Okay, so that's, or which best represents this set of data points. Okay. Or we could ask that I give you a full function with a set of ai's, okay, and what is the probability that these measured values, okay, are, or yi, what is the probability that yi is y, which is f of x plus or minus some given delta y, okay, some small delta y, or what is the distribution of this delta y. Okay, so that's the two questions which we can ask. Okay, that's what we should try to do. Okay. So again, to summarize, so we given a set of n data points xi and yi, okay, and we want to fit a function f of x, okay, through this data set of data points, and we have some adjustable parameters ai. Okay. So the question we are asking is, okay, so if you are given a set of ai's, okay, so the two questions which we could ask, okay, so that is how good is the given choice of ai's, that is if I given this functions this values xi and yi and an adjustable parameter ai, if we choose a set of ai's, how good they are. okay, or in other words, what is the AIs which will best represent this data if I put it inside this function f of x, okay, or given a set of AIs, if you given a set of AIs, suppose that is correct set of AIs, okay, suppose it is given to you a set of AIs, then what is the probability the data passes through the curve, okay, given by the function f of x with this set of AIs with an error of plus or minus delta y. So these are two precise questions which we can ask. Okay. So these two, with these two questions we can actually formulate, so keeping these two questions in this mind, okay, we can formulate a method of doing a fit, okay, and now this fit would be called as a chi-square fit, and we will see what that chi-square fit means in a few minutes. Okay, so now, so what we are saying is the following, that if we assume that each data point yi has an independent random error, okay, which is Gaussian distributed around the true model f of x. So what does it mean? So we have this model, okay, this is a model, right? So it's called real function, or that's why I put it in quotes. It's a real function in the sense it's a model. Okay, this is what we believe is the correct function is, and we now assume that the measured values, okay, since this is the real function, the measured values, that is yi's, are distributed around y in a Gaussian manner. What I mean by that is, if I take if I actually plot the probability of yi's, okay, the probability of yi's, okay, and then I plot it as a function of yi for different values of yi, okay, so this is okay, so that is this axis I plot the probability, and then if I put yi here, y axis, and then I would get some distribution like this, okay, some distribution like that is what I would get, and the peak of that distribution would be y equal to f of x. Okay. So that's what I mean by this, that is by it's Gaussian distributed. This is what I would assume. Okay. I would assume that an independent random error, okay, is what happens when I do the measurement. That is, the true function is actually this. This is a real model for the function, a model for the data, and when I should have got, for given xi, I should have got y of f of xi as my yi value, okay, but I will not get. I will get some value yi, and that measured value, and because it's a random error, okay, by random error, it will always be Gaussian distributed. Okay, so that's the assumption which you are going to make. Okay. So it's always Gaussian distributed or normal distributed. Okay, so that's what we are going to say. Okay. So remember, this is the what I am plotting here is the distribution of the yi values. Means if I take one, let's say x represents temperature, and this yi represents some quantity, some measured, some value which I can compute, okay, some conductivity, something like that, resistance or something. Okay, so this is the temperature resistance, and then I fix the temperature and I make many measurements of the resistance of some object, some wire, and I plot the value of resistance I get as of for different, the number of times I obtain one particular resistance, okay, as a function of resistance. Okay, if I plot that, I would get a distribution like this, okay, with where the peak is, with the peak corresponding to the real value. So it's distributed around the real value in a symmetric Gaussian way. So that's the assumption. Okay, the reason for this assumption is that we believe this error in this data is some random error, and by central limit theorem, what's called central limit theorem, you should always get a Gaussian distribution that if you make enough measurements. So that's what the assumption here is. Okay, so that's the first assumption which we make when we go ahead and do the fitting. Okay, the first assumption that we make is that the error in the measurement of yi is a random error, and it is Gaussian distributed around the true value, which is f of x. Now we also assume that the standard deviation of sigma of these distributions are the same at all points. Okay, this, for the time being, we make this assumption. Okay, that's what we are saying is, now if I change this x or my temperature to some other value, Okay. And so I would change the yi, right. If I change the xi, I will change yi. If I change the x, I will change the y in the true model also. Okay. So, and the distribution around that value is also similar. Okay. It has the same width, okay, and it is similar. That's another assumption we make. It's not a very hard and fast rule, and we don't need to make this assumption, and we can do without this assumption. But to simplify things in the beginning, let's make an assumption that this distribution is the same irrespective of what the value of x we choose. We choose another value of x, the distribution will shift, but it is only a shift, and the functional form will remain the same. Okay, that's what we assume. So that's what's been given here. So in short, he's saying that this probability, which for each of these xi's, let's forget this for the time being, each of these xi's, the probability is simply given by this. Okay. So the probability that I will erase this now. So in short, what I am trying to say is that this probability is given by P of y, or yi will be is equal to exponential minus half, so f of x, which I call y, minus yi, so that's what I am going to write, okay, divided by sigma square. Okay, so that's what I wanted to say. Okay, so that's a function value which I want to get, or the probability that I would find the yi value between plus or minus delta y is given by this multiplied by delta y. Okay, so this multiplied by delta y will give me the probability that in a given measurement I would get a value which is plus or minus delta y around the true value y. Okay, that will be given by this. So this sigma is my standard deviation, and I am going to assume that the sigma is same irrespective of what x value I choose here. So this y is, so this is the same as e to the power minus half f of x minus yi the whole square divided by sigma square. Okay, exponential of that, right? So into delta y. So what I am trying to say here is that this sigma is the same irrespective of what x I have chosen is. So then I can now say that what I have to, the total probability is now given by the product of all of this. So, okay, so now the product of all these functions from I going to 1 to n is the probability is that all given set of data points, okay, all values passes through the yi, passes the real function yi, the real function f of x within a distance delta y from it. So remember, so the question here is I give you a set of I give you a real model f of x. Now the probability that my measurements y passes through or is within a distance delta plus or minus delta y from the real value f of x is given by this. Okay. Now given a set of n points, the probability that all these n points are within a distance plus or minus delta y from the real value f of xi is given by this product. Okay, so p is equal to p is proportional to I going from 1 to n of this, right? So n data points passing through this. Right. So that's the function. Okay. So now what we need to do is this f of x, as we said. Okay, so now the full probability is what we are writing now as so the full probability which we are interested in is p proportional to pi. So that's a product function, right? Pi 1 to n. Okay, so I will say this is as f of xi. Okay, so that's a real value, but then that's a product which we are interested in. Okay, and this is what we want to minimize. Okay. So now when I given this, if I been given this data points xi and yi, what I want to do is I want to now find out this function f as some adjustable parameters ai's. I want to find out those set of values ai such that this is a minimum, right? So I means I want to sorry, this is a maximum. Okay, so that means I want to maximize the probability that it actually goes through the real function yi. Okay, so that's what I wanted to do. Okay, or I want to actually make the negative of this logarithm minimize, negative of this function minimize, right. So I want to basically make sure that this is maximum. That's why I said that negative of this logarithm maximized. Okay, that's what we want to look at this. Okay, so we want to make sure that this goes through, the probability that it goes through a value plus or minus delta y from the real function should be maximized. That means this minus of this quantity in the bracket which I am writing here should be, we want to make it minimum. Okay, so that's what we want to do. So that's what we have written down here. So what we want to do is to do this. Okay, so maximum probability would mean that this quantity here, this whole quantity, which is basically saying that I want to make this whole thing in the bracket a minimum. Okay, so exponential of this quantity is a minus sign here. So when you minimize this function would be maximized, right. So that is what we wanted to do. Okay, so maximum probability would mean minimizing this whole quantity. Okay. So and then we remember this, the f have all the adjustable parameters ai's. So what we want to do is we have to take this function, right. We want to take this function and minimize with respect to the ai's. Okay, now this is not a function of ai. So basically what we want to do is minimize this particular function, that is sigma I going to 1 to n yi minus f of xi, which also contains the ai's, divided by 2 sigma square. We want to minimize this function with respect to ai's. Okay, so that is the essence of what we call the chi-squared fit. Okay, so now we are going to define the chi-square as just that quantity in the bracket. Okay, so basically this is my chi-square. Okay, so this quantity is what I am going to call as the chi-square. Okay, so you can see that that is a chi-square which I have written here. Okay. So it is that that every point xi yi. Okay, now we could assume now we could get rid of even that as a particular assumption which we made, that each point xi yi had the same error or the same standard deviation. We can get rid of that, and we can say that each point xi and yi had a standard deviation sigma I. Okay. And then I could define this now as yi minus f of xi divided by sigma I the whole square, I going from 1 to n, and that is what my chi-squared would be. Okay, what's called a chi-square. And now what I have to do is minimize this chi-square with a function of ai, and that's called a chi-squared fit. Okay, so we would call a chi-squared fit, and you would see this almost everywhere in science and engineering. Okay, so now we can minimize this. You said, okay, I can take this chi-squared. Okay, so what I'm going to do is I'm going to take this chi-squared, right, which I defined as f of xi minus yi the whole square divided by sigma I squared. Okay, that's what my chi-squared is. Okay, now f contains all the ai's, and I'm going to minimize this. Okay, so basically I would do del by del ai of chi-squared equal to 0 to minimize this function for all ai's. Okay, and I would find out what the ai values are. So now, and then I find some ai values and I put it back into this function. Okay, and I can calculate this chi-squared. Okay, so how do I know which is a good fit or not? Okay, what is the kind of thumb rule? So the thumb rule is that for a good fit we should have chi-squared of the order of n minus m, where n is the number of data points and m is the number of adjustable parameters in the fit. Okay, so that is a chi-squared rule. So remember that if we did not know sigma i's, okay, and if you knew the real function f of x and the measured value is y of I, yi, then we could have actually computed the sigma as in this fashion, right? yi minus f of x whole squared, sigma I going from 1 to n divided by n minus m. So that would be our standard deviation by standard definitions. So now the question is, now we want to do this fitting. So we'll take a particular function and then do this fit. Okay, so now we need to know what the functional form of this if you want to do this, right? So so far we said the general model f of x is contains some function, some parameters ai, and we can define a chi-squared like this from the measured value and the real function divided by sigma I square, and I can minimize this chi-squared with respect to all the ai's. Okay, so all for I going from 1 to m. Okay. So, I could minimize this, where m is the number of fitting parameters which I have, and I could write this equation and I could solve this equation for the AIs, and then I would get a model. But now so far we have not said what f of x is. Okay. So, f of x could be a nonlinear function, a linear function, it could be any of this. Okay. So, now we will take a specific example and do this, a specific set of functions. So, first we will do is a linear function. So, we will assume that f of x is a linear function of x, okay, and then we will actually solve this model and see how to determine the a values are. That is what we are going to do now. So, basic philosophy is now just this, to do this. Okay. So, we have taken here a set of values f of xi. Okay. So, we have f of x as ax plus b. Okay. We took this f of x as a plus x plus b, and now we can define the chi-square as that. Okay. And then we can minimize this function. So, that is what we are going to do. So, we said f of x is ax plus b. Okay. So, that is our function, and we can define now the chi-square would be then equal to yi minus ax minus b the whole squared divided by sigma I squared. So, that will be our function sigma okay, actually this 2 does not matter. So, that is what we would have. Okay. And then we could just minimize this. So, we can minimize del chi squared by del a, right. So, that is what first thing we should do, right, and then axi, sorry, okay, and then we have to do del chi squared by. So, we will get, if you do this, we would get sigma yi minus xi divided by sigma, oh, sorry, that is okay. That's what we get if I just minimize with respect to a. Okay, and then I have another function which will be del chi squared by del b. So, that will be again sigma I yi minus that's minus sign again. Okay, that is the quantity which we would get. So, we want to equate these two to 0. Okay, so, if you do this and if you can solve these two equations. Okay, so, you have sum over I going from 1 to n, all the data points 0 to n minus 1 or 1 to n. Okay, and we want to solve these two set of linear equations. In it is linear in a and b, right. So, it is a set of linear equations we want to solve, and we want to get a and b. Okay, that is what we are going to do. Okay. So, that is summarized here. So, we just minimized with respect to a and b, okay, and we got these functions which is written on the board here. So, that is yi minus axi minus b by sigma I square into xi, and so this 2 does not matter actually, and then yi minus axi minus b by sigma I square. Okay. And then now we will just, what we do is we would come with some parameters to, so we have to first compute yi by sigma I square, xi by sigma I square, and or yi into xi by sigma I square, xi square by sigma I square, 1 by sigma I square, and we sum each of them from 1 to n. Okay, similarly here, and then we would write it in terms of a set of parameters on this in this fashion. Okay, so now that's given here. Okay, so these equations which we had, okay, now we will write, just concentrate on this. So this is, we would come with some new set of parameters which is s as sum over I from 1 to n, 1 by sigma I, and sx as xi by, actually sorry, this is sigma I. So, we'll write all these functions here. Okay. So, we would use yi. So, we want to have sigma I xi yi by sigma I squared. We want to compute that, and then we want to compute sigma I xi squared by sigma I squared, and we want to compute sigma I 1 over sigma I squared, and we want to compute sigma I yi by sigma I squared. Okay, so and sigma I xi by sigma I squared. So all that finishes all the quantities we compute. We will first do that. That will be the algorithm. First we will do this xi yi by sigma I square, because they are all known to us, and xi square by sigma I square, xi by sigma I square, and yi by sigma I square, and 1 over sigma I square, and we call this as sxy, and we call this sxx, and this as s, and this as sy, and this is sx. So now I can rewrite this set of equations in terms of these parameters. Okay. So I can write down, I can use these functions, okay, and then plug them into my main equation and write it in, put it into this equation and write it in a different fashion. Okay. So I just substitute all that, and then I will get a set of equations which are given by this. Okay. So if I just do that in terms of sxy, sxx, sx, sy, xx, and s, I can write it in terms of two linear equations, and I can solve them and get a and b. Okay, so that's the algorithm. So it's easy to compute in that way. Okay, so for a general linear fit, we can compute it using these two linear equations. Okay, and I can solve for that, and then I get a and b as s into sxy minus sx sy divided by s into sxx minus sx square, and the same denominator here, and sxy minus sxx sy divided by sx square minus s into sxx. Okay. So if I have defined a and b in that way, so I can solve these equations and get a and b. Okay. So then once you have these functions a and b, then the next question would be what is how reliable this a and b is, and so we need to define what is the error or what is the deviation in the a and b itself is. Okay, so that we would get that's what we would next go into. But before we go into that, we will actually see the implementation of this particular form of linear fit in a program. Okay, so that's what we will do next. We will now look at the implementation of this fitting a linear function into a given set of data. We will, as we go along, we will also pay attention to the programming details. So here is a program which would implement the following. So we have a set of function values given at xi and yi. So instead of an array, this program I am using a pointer x and y, and then as I said in the case, that what we want to fit is a function f of x is equal to ax plus b. So we have defined our chi squared as y minus ax minus b whole square divided by sigma I square, and we have to minimize this chi squared with respect to a and b, and we now and then we get this set of equations, and to program these equations or to write an algorithm for this, solving this, we first define yi by sigma I 1 over sigma I squares, and yi by sigma I squares, and xi square by sigma I square, etc. in this set of functions s, sx, sy, sxx, syy, sxy, etc. And then so we want to compute these quantities first. Okay, that's what we are trying to do first. Okay, so here is that code. So we are defined as all of them as floating point numbers, and we said they are all set equal to 0 to begin with. Right, and then now we want to read this x and y, that is the given set of points x and yi from some file, data file. So I call that data file as fit.data, okay, and then I can open that file. So I open that file using this function pointer, the file pointer an array which is x and y. So before I can put it into x and y, which is a pointer here, I have to allocate memory to that memory for that pointers, and that's what I'm doing here using this malloc function. So there are floating points, so I'm allocating memory to that using float star malloc and some n. So that is what I'm doing here. Okay. So we have gone through this before, so I'm just showing you the implementation of that in a real program. So here is the x and y being allocated some memory. Okay, and then I use the scanf function, the fscanf function. After opening this file, I use the scanf function to actually read this the values. So the function values are tabulated in what's called so fit.data. So here is the x in this form. I have tabulated this function values, the xi's and yi's. Okay, so I have them here. Okay, and I'm just reading that off in this using this fscanf function, and since they are floating points, I use percentage f, okay, to read them. I have to read them into two variables x1 and y1, which I declared as floating, and I store them in this arrays xi and yi, which is now I can store them because I have allocated memory into that x and y. Okay, so that's important. So you need to allocate memory first, and then I store them into that. Okay, so I just print that out. When I run the program, I just print it out on the screen, the xi, just to see that everything is all right. And then I have the red values, and then I again print them out the xi's and yi's here. So, and just to show you that what we have read is exactly the same as what has been put in. Okay, just to help us in debugging the program if there is any bugs. Okay, so now that's a little programming detail. Okay, so then we go into the calculation of s, sx, sy. So we have initialized all of them into 0. Okay, so and then we compute the s sigmas. We are not in this data given to us. The sigma is not been given. Okay, so we assume all the sigma to be 1. Okay, all the sigma is same, so we just assume them to be 1. Okay, so we could put any number in this thing because sigmas all of them are the same. So we just assume them to be 1. And then we just so I just put them as that itself. Okay, so we can just put s as s plus 1. Sorry. Okay, so s as 1. So I just have to sum over all the i's. So sorry, this is 1. Sorry. And then we have sx and sy. So sx being as since sigma is 1, I just said sx is x of I. Okay, so remember sx is x of I by sigma I, so this is sigma I, xx by sigma I, but then sigma is 1, so it's just x. Okay, so sx is x. Similarly, sy is just yi, and sxx is xi into xi, and syy is yi into yi, and xy is xi into yi. Okay, so this is summing over all the points. Okay, so remember we have to initialize them first before you do this sum, and we have done that in here, okay, in the declaration itself. Then we compute the denominator. So we need to compute. This is the solution which we get, right? We know that. Okay, we substitute all that. We get an equation like this, and the solution is this. So we compute the denominator of this function. Okay, and then that's first, and then we can compute a and b. So I computed the denominator here, and then I can compute a and b in this function. Okay, so that's what we will do, and then we will look at a fit of this function. Okay, so that's what we will just run this program now. So we compile that, and then we run this program, and we get the a and b values as, so this is printing out the xi and yi values, and the a and b values as 3.33 and 0.069174. So that's the a and b values which we have got. Okay, and we could plot this. Okay, so I'll just plot them now. Okay, and that's a plot. So this is the value, and so that's this. Again, the circular points here are the values which are tabulated, and the straight line going through is my fit for this given value ai. Okay. So then we can actually, so we have as a and b, okay, and so we have a straight line. So given for this spread of values with the same sigma i's, we said that all of them are, all the points here have equal reliability, and then we have this straight line which goes through these points, okay, which is the best fit to this point, or best chi-squared fit to this point, okay, the set of points. That's what we have. Okay, so now next question obviously is, so what is the error in the, how good is my fit, right? So that's the question which you would ask. Okay, now we have an estimate for A and B, we have got A and B. Now can we try to estimate errors in the parameter A and B, okay, given obtained by such a fit? So then we have to recall something which we learned in the beginning lectures, that if there is a function which is a function of x, let us say, and if there is an error in x, okay, given by some delta x, okay, and then how does that error in x propagate to the function value itself, right? So that's something which we learned before, and we said that if there is a function of x and x is a floating point representation, in that context we had learned that. So there is an error in the representation of x, which is given by delta x, let us say, and then the delta f, that is a error in the function value f, okay, because of the error in x is given, delta f is given by delta x into derivative of f with respect to x. That is what we had seen. So same thing which we can use here. We are looking at what would be the sigma in the function, okay, and if given some function f, given that the variables there had an error sigma I, okay, and then you would say that it is, you know, sigma f squared is sigma f would be given by sigma I into derivative of that thing. We are taking the square here, but derivative of that thing. So sigma f would be sigma I into derivative of that function with respect to I. So here we are looking at the errors in A and B. A and B are obtained now as functions of xi and yi, right? That's what it is finally. Okay, so the question is, what is the spread in the yi? How does that affect, or how does that give us a spread in A? Okay, so that is what we given by sigma A squared, right? So sigma A square is then sigma I square, which is a spread in the yi's, okay, multiplied by derivative of A with respect to y whole square. Okay. Similarly, the spread in the B, sigma B squared, would be the sigma spread in the I, the spread in the y, which is sigma I squared into derivative of B with respect to y squared. Well, that is what we would get as the sigma A square and sigma B square. So remember, we can actually, if you go and look back, look at this, we see that the A and B are actually represented as Sx, Sx, Xy, Sx and Sy, etc. And these are functions of yi's, right? So these are functions of yi's. So we can actually compute the derivatives of A with respect to y and derivative of B with respect to y from these functions. Okay, and it's possible to compute these values of sigma A squared and sigma B squared. So that is, and having, so because we can actually evaluate derivative of A with respect to y from that expression which we just saw, and derivative of B with respect to y from, and so using this we can actually compute sigma A and sigma B. Okay. So now, so if you do that computation, then we would find that sigma A squared is simply given by S over delta, or the delta is that Sxx minus Sx square, which we just now saw. So and sigma B square is Sxx by delta. Okay. So we can actually not only get estimates for, or the values for A and B, we can even make estimates for the error in A and B, in sigma A square and sigma B. Okay, so now what is the implication of this is that if the spread of the data around the line is similar in magnitude along the entire range of the data, okay, or the distribution of the points along the line is normal. Okay, now these two, why I said an if here is because these two have been assumed in our actual derivation of the data. Okay, so these two have been assumed in our actual derivation of the data. So the derivation of the points, that is the spread is normal. Okay, the yi is normally distributed. That's it's Gaussian. We assume that. Okay. Then we can define as now we can define a standard deviation for the regression line. Okay, that's fit. Okay, for that we can define a standard deviation, and that is called a standard error of the estimate. Okay. So to summarize, so we see that we can not only compute this A and B, we can also compute the errors in A and B, that is sigma A square and sigma B square, okay, and we can write them as a very simple function of in terms of S and delta as S by delta and Sxx by delta, okay. And then we can define what is called a standard error for the fit, and that is given by as chi squared by n minus 2. Okay. Now, that is a definition of the standard error, and this error is, we can define that only if the y distribution is Gaussian, that is for a given x value, if you make many measurements of y and if the y distribution is Gaussian, then we could define a standard error as given by sigma as chi squared by n minus 2 for the fit. Okay. So, chi square is something which we get from the fit. Okay. And then the spread in the data, we can define another quantity called a spread in the data, which is yi minus y average squared by n minus I squared. Y average would be for a given x, as we said, there is a spread which is Gaussian, and you take an average of that. Okay. So, that is the yi, and yi is one measured value, and so that gives us a measure of the spread. So, now given these two quantities, so remember sigma d here is a spread, which means that for a given value of x, that is like give a fixed temperature, we make many measurements, okay, and then we take an average, and if we take many measurements, we get a spread, we get various different values of yi's, and that yi's we believe are Gaussian distributed, okay, and that and then we can take an average of that, and then the average and yi minus that y average whole square divided by n minus 1 is what would be what we call the spread in the data. Okay. So, yi minus y average square, okay, that is like a mean square average, a mean squared distribution, mean squared y value. So, given this chi square and sigma d squared, we can define another quantity called a correlation coefficient, and that is given by sigma d square by chi square by sigma d square. So, I am just giving you a set of quantities which is computed as a standard thing when you do a fit. So, one is the correlation coefficient, for which all we need to know is the sigma d squared and chi squared, right. And so then we can compute sigma d squared minus chi squared by sigma d squared, and then we can also compute what is called a standard error, which is chi squared by n minus 2, and we can then we can compute the errors in the A and B as sigma A square and sigma B squared. Okay. This is all apart from just computing A and B itself, which is the fit to the given set of data for a function f of x, f is equal to ax plus b. Okay. So, we can generalize this idea into a general linear fit. So, now we have just done this particular quantity, that f of x as ax plus b. We will generalize this this algorithm into a general linear fit in the next lecture. That is what we will be looking at in the next lecture.